Hello everybody, welcome to my talk. I'm going to tell you how to find large H-colorable subgraphs in hereditary graph classes. The results obtained here are joint work with Maria Czudnowski and Jason King from Princeton, Michał Pilipczuk from Warsaw, and Sophie Spirk from Waterloo. And she was in Princeton when we were working on that. When we are dealing with computationally hard problems, a natural thing to do is to try to restrict input instances to see when the problem becomes tractable. And a rich family of such restricted instances comes from considering graphs with certain forbidden substructures. In particular, we will be interested in something called F-free graphs. So F is a fixed graph, and we say that a graph is F-free if it doesn't contain F as an induced subgraph. So the graph on the left is not P4 free because there is an induced copy of P4, while the graph on the right is P4 free because every P4 is not induced. So those classes are hereditary, meaning that they are closed under taking induced subgraphs, or equivalently under vertex deletion. And similarly, we can define F1, F2 up to Fp free graphs, meaning that we can forbid more than one fixed graph. Considering those classes is a very active area of research recently, both from structural and algorithmic point of view. And when you look into the results about complexity of certain problems in those classes, quite quickly you see that there is some peculiar case of PT-free graphs, so graphs that exclude a fixed path as an induced subgraph. So it appears that for many canonical problems, we don't understand the complexity when we restrict to those graphs. So, for example, for independent set, we know polynomial time algorithms only for very small values of t, and currently best result is for P6 free graphs, and that's SODA last year. If we are a bit more modest and we don't ask for a polynomial time algorithm, we know that for every fixed t, the problem can be solved in subexponential time, and with a recent breakthrough by Lokshtonov and Gartland, we know that the problem is actually quasi-polynomial time solvable. So, on one hand, the structure of these PT-free graphs is rich enough to make the design of algorithms difficult, and on the other hand, it's not rich enough to devise some kind of hardness reduction. So all hardness reductions for independent set that we know produce long induced paths. There are more examples of problems like this. For example, free coloring. Again, it's polynomial time solvable for P7 free graphs, and this is the result from SODA 2 years ago. Again, this problem is subexponential time solvable and even quasi-polynomial time solvable for all t, but we are very far from obtaining polynomial time algorithms for all t. Similarly, is for feedback vertex set. Very recently, it was shown to be polynomial time solvable in P5 free graphs. We also know that it's subexponential, but for all the problems I mentioned, we don't know any hardness proofs. Why I'm showing this to you? To show you that even for small forbidden paths, the problem becomes difficult. As you can see, those results are very recent, and also they appeared on some top conferences, including SODA and Fox. And those algorithms are really difficult to obtain. So one might think that when we, for example, forbid P5, it's a very small graph, so it should be a very simple class of graphs, but this is not the case. This class of graphs is actually quite difficult to understand. The problem I'm going to tell you is odd cycle transversal, which asks us to find the smallest set which hits all odd cycles. So in other words, we can ask for the smallest set whose removal makes the graph bipartite. So, and this problem is not like the problems I mentioned so far. So this problem is known to be polynomial time solvable in P4 free graphs, but it's not surprising because P4 free graphs are really simple. In particular, they have bounded click width. And we know that for P6 free graphs, this problem is hard, meaning that it's NP-complete. And also, if we assume the exponential time hypothesis, there is no sub-exponential time algorithm. So there is an obvious missing case. What is the complexity of odd cycle transversal in P5 free graphs? And this problem was our original motivation. And long story short, we are not able to answer this question, but we obtained several nice side results, and I'm going to present one of them to you. So the first result I'm going to mention is an algorithm for odd cycle transversal in P5 free graphs with running time n2 of omega, where omega is the click number of P5. So in particular, this algorithm works in polynomial time for graphs that are P5 free and have bounded click number. And before I go to the proof, let me mention that we cannot hope for an extension of these results to P6 free graphs, because this hardness reduction I mentioned actually creates P6 and K4 free graph. So they have a bounded click number. The crucial combinatorial structure that we use in our algorithm is something called monitor. So a set is called a monitor if, let's call this set S, if every component of G minus S has a vertex in S which is complete to this component. And the property that we are going to use is the following. If we find a set S that is a monitor, then every connected component of G minus S has a smaller click number. And let's see this is really the case. Let's C be a component of G minus S and consider a maximum click in C. So since S is a monitor, we know that there is W in S, which is complete to C. So in particular, it is complete to this click. So this gives us a larger click in G. And the lemma that we prove that is that if you have a connected P6 free graphs, so notice that here it's P6, even though we only need P5, then there is a set, a constant size set, a set of size at most 3, whose closed neighborhood is a monitor. So by closed neighborhood, I mean this set and all neighbors of those vertices. The proof of this lemma is actually not very difficult, but I'm not going to show it. I'm going to show how to use this lemma. So assume that we know this. And let's look at a connected P5 free graph, and let's try to understand the structure. So by X, we mean a set from the lemma, so we can assume that it has exactly 3 vertices, x1, x2, and x3, and we know it is a monitor. Sorry, the neighborhood of this set is a monitor. And for each I from 1 to 3, I define the set AI. And the set AI is the set of vertices that is adjacent to xi, but is not adjacent to any of the previous x's. So I somehow fix an ordering of those x's, and I partition their neighbors with respect to the smallest x that they see. The important thing is that there are no edges from x1 to A2, from x1 to A3, from x2 to A3. And I also introduced the set A4, which is the remaining set of vertices. So those are vertices that are not adjacent to anything in X. And what is the high-level plan? I would like to look at the graphs induced by those sets A1, A2, A3, and A4. And I claim that each of them is still P5 free and has a smaller click number. So of course it is P5 free because it's an induced subgraph of the previous graph. And why the click number? For A1, A2, A3, it's clear because if there is a click in A1 with X1, it produces a bigger click in G. And in A4, remember that the closed neighborhood of X is a monitor. So whenever we take some click in A4, it lives in some connected component, which means that there is a vertex in the monitor which is complete to this connected component. So this gives us a larger click in G. And our high-level plan is to guess the solution in X. I can do it because X is a constant size set. Do some kind of cleaning and run our algorithm recursively on each G of AI. So if we manage to do this, this will give us the claimed running time because the click number drops. The only problem is that we have plenty of edges between those sets. So we need to somehow get rid of them or make them meaningless in our problem. And this is what we are going to do next. So let's suppose that we have some kind of optimum solution. So S is the minimum odd cycle transversal in G. And we know that when we remove S, we obtain a bipartite graph. So let's fix some bipartition of this graph. I will call those vertices black and white, and I will denote those sets by B and W. So actually, we can look at our problem as a partition of the vertex set of our graph into three sets, B, W, and S, such that B and W are independent and there is no restriction on S. We only try to make it as small as possible. So I will actually think of some kind of least version of this problem. So if for some reason I decide that some vertex cannot be black, I will just remove B from the list of this vertex to keep in mind that this set is forbidden for this vertex. Okay. So the crucial claim in our algorithm is the following. For each I, 1, 2, 3, when I look at the black vertices in AI, there is a subset BI of those black vertices in AI with two properties. First, if some vertex with the set with a larger index has a neighbor, has a black neighbor in AI, then it has a neighbor in BI. So in some sense, BI hits all neighbors of black vertices in AI. And also BI is small, and it's actually at most two vertices. And there is nothing special about the color black here, so we have exactly the same claim for white vertices. So let us prove this claim. So recall, this is our setting. We have the set AI. A is 1, 2, or 3. We know that there is vertex xi, which is complete to AI. And on the right, I have vertices from sets with larger indices. And I know by the definition of those AIs that there are no edges from xi to the right set. So let's take B prime to be the inclusion-wise minimal set satisfying the first property. Clearly it exists because I can take all black vertices in AI and they satisfy this property. And let's see what happens if this set has at least 3 vertices. So first, B prime is inclusion-wise minimal, meaning that every vertex in B prime is needed. This means that each of them hits one guy on the right, which is not hit by anybody else. This means that each of them has a private neighbor in the right set. So I have this 3-element matching, and there are no more edges between the left vertices and the right vertices. Next, recall that B prime is the set of black vertices, and black vertices form an independent set. So there are no edges between the 3 vertices on the left. So now let's see what happens. If at least 2 vertices on the right are non-adjacent, then I have a P5, induced P5, like in the picture. So suppose that this is not the case, so that on the right we have a triangle. But then we have another induced P5. So whenever B prime has at least 3 elements, then G has induced P5, but G was P5 free. So it's a contradiction, meaning that B prime can have at most 2 elements. Good. So equipped with this claim, we are ready to present the algorithm. So let's recall the structure of the graph. It's depicted in the picture. So first, I guess the solution on X. So I have 3 vertices. For each of them, I have at most 3 possibilities because it could be either black or white or deleted. So I have a constant number of choices. And when I update the lists of the neighborhood of X, I notice that I no longer need those vertices. So for example, if xi was colored white, this means that no vertex in A1 can be colored white. So I can remove white from the lists, and there are no other restrictions. So after this step, I can just remove the set X. Okay, so now I need to deal with those remaining edges between the sets. So for each I, 1, 2, 3, I guess the sets BI and WI that come from the claim. And the claim says that they have at most 2 vertices, so I have at most 12 vertices to guess, which gives me n to 12 possibilities. And now let's consider an edge between 2 sets. So if some vertex from A with a larger index is adjacent to some vertex in BI, this means that it cannot be in B, because B is an independent set and BI will be the vertices that are colored black. So I can remove color B from the list of V. On the other hand, if somebody in A with a larger index is non-adjacent to any vertex in BI, this means that none of the neighbors of V in AI might be black. Why? Because BI hits all neighbors of black vertices in AI. So if I have this situation, I can remove black from the vertices in AI that are adjacent to V. And when we do this for all vertices, we notice that all the restrictions coming from the edges are already encoded in the lists. So I no longer need those edges. I can remove them. Oh, sorry, of course I do the same for white vertices. So after updating the list, my instances are independent. I remove the edges and I can apply reduction on each of the recursion on each of those 4 graphs. And when I do the numbers, I get the running time n2 of omega, which is what I wanted to have. Good. It appears that this algorithm gives us one more nice corollary, which is that we can solve odd cycle transversal in P5 free graphs in subexponential time, in time n2 of root n. Notice that there is no click number here, so this is just P5 free graphs without any further assumptions. And this algorithm is rather standard. We employ a win-win strategy. So first, we consider the case that G has a clique of size larger than root n. So this is a clique, and black vertices are independent and white vertices are independent. So at most one vertex of this clique might be black, and at most one vertex of this clique might be white. I can guess those 2 vertices, and the rest of the clique must be removed. So this gives me this type of running time, and we conclude that the first case produces n2 O of root n instances when each clique has size at most root n. So what happens if we deal with an instance with clique number at most root n? We just apply the algorithm that I showed you before, and it can solve the problem in time n2 O of root n. And this gives us the claimed running time from this theory. Let me point out that, again, there is no hope to extend this algorithm for P6 free graphs because, as we pointed out, there is no subexponential time algorithm for P6 free graphs unless the ETH fails. So let me now discuss some possible extensions of this algorithm. So first of all, it works in the weighted setting. So instead of looking for the minimum odd cycle transversal, we can ask for an odd cycle transversal with the minimum weight. And actually, when we look at this problem, we notice that we are not really interested in finding hot cycle transversal. There is nothing special about this bipartite graph that is left here. The problem that we are solving is we are looking for k pairwise disjoint independent set such that their total size or weight is maximum. Or equivalently, the total size of the set that is not in those independent set is minimum. So the problem that we are solving is actually max k colorable subgraph for fixed k, and if k is 2, we get precisely hot cycle transversal. And it was already known that k coloring is polynomial time solvable in P5 free graphs, and actually this algorithm is quite similar to our approach. So we took inspiration of this algorithm, but we were able to push this method for a more general problem. If we look at this problem even more closely, we notice that we can solve even more general problems. So we can fix an irreflexive pattern graph, and we ask for a maximum sized subgraph that admits a homomorphism to H. So it's H colorable. I will not define this problem because it's not so important for the purpose of this talk, but this is the setting that we work with. And finally, the branching that I showed you is kind of simplified. In the paper, we have a more involved branching, which allows us to obtain more algorithmic results. And some of them are listed here. For example, we can solve our problem in P5 F-free graphs in polynomial time when F is a threshold graph. Or we can solve the problem in polynomial time in P5 bool-free graphs. Finally, we can even solve the problem in P6 one subdivided claw free graphs, but now the running time is not polynomial, but it's again n to some function of the click number. Now it's omega to the third. We also have several other results that are not listed here. Okay, let me conclude my talk with pointing out some interesting directions for future research. So the first, recall that we started with a problem of odd cycle transversal in P5 free graphs, and we are not able to solve it. So the big question remains open. What is the complexity of the problem in P5 free graphs? Everything hints that it should be polynomial, but of course, we don't know it. Second, recall that the algorithm that I showed had running time of the form n to the click number. And we think this is an interesting setting to consider. So maybe there is a hope to obtain similar algorithms for other problems whose complexity is not clear for PT-free graphs. So we think this is an interesting approach because it could be a nice setting for recursion. So you can do some cleaning and do some recursive call, and in each call you either reduce the length of the path, which is quite standard thing when you work with PT-free graphs, or you reduce the size of the maximum click, similarly to what we are doing here. Let me point out that similar problem was considered very recently by Britell and others. So in particular, they proved that if you forbid any fixed path, any fixed click, and any fixed one subdivided star, then your graph becomes quite simple. In particular, it has a bounded mean width. So for those graphs, we immediately get polynomial time algorithms for many natural problems. The problem is that this bound is large, so they don't get a nice running time. They get polynomial, but the degree of this polynomial is huge. And the last problem that I'm going to mention is the following. When we look at our problem as maximum k colorable subgraph, the number of those sets that we want to partition our graph to, so k, goes to the exponent of the running time. And we conveniently hide it in the O notation, but it could be large. And this is also the case if we consider a simpler problem of k-coloring. So we think that it would be interesting to investigate whether we can obtain an FPT algorithm for k-coloring in P5 free graphs when the parameter is the number of colors. Thank you for your attention, and have a nice rest of the conference.